Thank you to Patrice and Professor Lee for the presentation. So we are open for questions. I can maybe start. So you made the control mock-up to validate design principles. Did it indeed validate them, or did you make any changes on your original design after the control results?
Okay. Yeah. Thank you very much for Niels for your question. Yeah, you are right. The 1.5 megawatt co-flow model was used to validate the design, but after the co-flow model, we did some change of the original design. But the original design was just a concept design. After co-flow model, we changed some reactor size, reactor height, and the solid collection details, something like that. Yes, very right. Yeah. But the critical issue, we didn't change the critical issue. For example, the overflow principle was not changed. The primary R and secondary ratio was not changed. Yeah, critical issues were kept, but some other additional issues were changed, were updated, or improved.
Okay, thank you. Any questions? Adam?
I have a question. If the fuel contains ash, how it is separated from the ilmenite or the oxygen carrier?
You mean ash separation from ilmenite? We can show this table. For the ash content, the ilmenite is only about 3.61, almost 4%. We can see also here the moisture for ilmenite is about 34%. With our test, after classification, the ash particle is very small size. The particle size will be smaller than 50 micrometer. So when the particle size is smaller 50 micrometer, it will collide from center. Yeah, but at the same time, there are also some possibility of slide. If we fit the ilmenite particle larger, for example 3 or 4 millimeter, there are some possibility for very big particle will be located at the bottom for area of fuel reactor. In this case, we will discharge the very large particle from the reactor bottom.
More questions? I think we have time for one more question. There is one. Well, apparently everything was very nice and clear to be presented by you. So thank you for your presentations. And we move on to the next presenters, which is Oyvind Langorgen and Lady. They will talk to us about the materials used to transfer oxygen in the CLC demonstration unit. So, please.
Thank you very much, and good afternoon, ladies and gentlemen. We will give a presentation about the materials used to transfer oxygen in the CLC demonstration unit. and it's me, Oyvind Langorgen from SINTEF. I have been the project leader or the leader of the work package 3 in the CHEERS project. And together with me is also Liu Lei from Tsinghua University. But this work is a joint effort between many contributors. The main contributors are listed on the front page. Kristina, Nicolas, Arnold from IFPN, Yngve, Swan, Inge, and myself from SINTEF, and Liu and Professor Lee from Tsinghua. And there are more people. So now we have talked about oxygen carrier already in the former presentations. They have mentioned ilmenite, but ilmenite was not the chosen candidate from the beginning. So this work was to choose the right candidate for this demo unit. And the right oxygen carrier is an extremely important part of the CLC process. It's one of the cornerstones of the process. It takes up the oxygen in the air reactor, as you have heard already. This is a very rapid oxidation at high temperature, about 1000 degrees in the reactor. And this oxygen is brought to the fuel reactor where it is used to combust the fuel. The oxygen transfer materials, or oxygen carrier as we call them, they do also transfer heat to the fuel reactor, because the fuel reactor is not so exothermic, so it will need some heat from outside to sustain the combustion process. And these oxygen carriers we are talking about here, there are mainly made of metal oxides from iron, from manganese, calcium, and copper. Nickel has also been used. They can be of two main types: natural minerals or ores that you can find more easily and less costly, and you have to do some treatment, but not so much. And then we have more advanced materials, what we call synthetic materials. They be produced in laboratories by chemical and metallurgical processes. They will then be more expensive, but hopefully also better value for money, hopefully. I can have two other comments to this basic concept of the CLC figure. The heat is generated mostly in the air reactor, which is the clean reactor, as was mentioned. This means, for example, for biomass fuels that contains a lot of alkali that can have severe hot temperature, high temperature corrosion issues, you will avoid that. That means you can increase your steam temperature for biomass compared to conventional technologies and gain efficiency. That is one thing which is special for CLC, which we should have in mind. Then we have also heard about carbon capture rate. And what is carbon capture rate in CLC? It's not so obvious from this figure, but as Professor Lee mentioned, you can have carbon or char particles from the fuel that are not fully converted in the fuel reactor, that will flow with the oxygen carrier back to the air reactor. There they will burn immediately at this temperature and high oxygen concentration, and you will have a CO2 stream out here. If this CO2 stream is zero, you can achieve 100% capture efficiency. And if this increases, your capture efficiency is reduced. So this is capture efficiency in CLC. So in the work in CHEERS related to this, we have done a lot of work on the lab scale to do screening tests. They have mainly been at SINTEF in Oslo and IFPN in Lyon. We have developed some materials, some synthetic materials, and based on the results there, we have chosen some candidates that we have produced in a larger scale that we could operate in the pilot units at IFPN, the 10 kilowatt already mentioned, and the 150 kilowatt at SINTEF in Norway. So, the important properties for the oxygen carrier material is, first of all, it has to transfer enough oxygen from the air to the fuel reactor. Then it has to provide high fuel conversion and also have a high reaction rate in kinetics towards the fuel, especially in the fuel reactor, which is the slow part. Then the lifetime is an issue. It's a cost issue and it's an operational issue. You can have materials that are truly have poor stability, both mechanical or chemical, or you can have good ones. And then cost availability and the cost of the material. So this figure here is showing an automated TGA system, thermodynamic analysis at CLC. This is used to map oxygen transfer capacity, and this is done by doing automated cycling. This is a full sequence of about 17 hours. Then you start to cycle the material, going down, then it is reduced, the oxygen is released by flowing fuel gas, then you change and flow an oxidizer gas, then the rate increases and they go up, and then you do this for 20 cycles in high oxygen concentration, then you reduce the oxygen concentration to the same and reduce even further, and then you repeat the same with less fuel gas concentration. This is to mimic exactly what Professor Lee mentioned, that within the reactors we have different concentrations of the oxygen across the air reactor. This we are able to capture in this rather simple setup, and we can also have different concentrations of fuel. Another thing is the stability, as I mentioned, and the picture here is showing some microscopic analysis, SEM EDS, so we can study the particles before and after use, and we can see, for example, are they getting very porous after use. We can also see all the different components of the material. Here, for example, we see a lot of green, which is manganese, but also some red, which is iron. So we can, from these pictures, also give a good judgment of how stable will they be in a more realistic setup. So, the materials we have tested in the CHEERS project, they are mainly ilmenite materials and different iron and manganese ores, that they are the natural minerals we have tested. And then we have produced some synthetic materials, iron, titanium, manganese, silicon, but now I will focus on the green ones here, which are the three most relevant candidates. And on the synthetic ones, it's a perovskite material made on these four compounds. And here you see an example of an oxygen carrier material in CLC. They will generally be particles, because we are talking about fluidized bed CLC here, of a size of about 200, 400 to 300 microns. So the materials we are going to use will have to be like this. So starting with the ilmenite then. Ilmenite in its reduced form is FeTiO3. And we have some different candidates. And just to make a short conclusion here, there is some ilmenite from Norway, from a mining site in Norway, Titania, that all performs all the tested ilmenite sources, that bear some ilmenite sand from other places. And here we can clearly see how the ilmenite have rather large amplitudes. That is a high oxygen transfer capacity, and it does not change very much when we change the oxygen concentration or we jump to a lower fuel concentration. And we do this at also at different temperatures, so very good this is automated. The other one here is much poorer, so it was discarded based on this. However, there are two types of ilmenite from titania. We call them T1 and T2 in this project. It's not an official trade name, so we cannot search that for Google, I think. But the T1 has a very broad particle size distribution, and the T2 is much more narrow and larger particles. And when we look at the wanted size fractions for the demo unit, we see that the T2, there we can utilize almost a whole batch, whereas in the T1, we can utilize just a small share, and we get a lot of waste material. So we would very much like to go for this T2, if we could, but we had some severe agglomeration issues during the first testing, and it was originally discarded as a candidate. Then some word about the perovskite synthetic material, and Leolé will say more about this, because they have made most of the testing on this. But this material was made by Syntef in Oslo. It is composed of commercially available basic materials that you mix together, you heat treat them, and by some magic reason I don't know, they get into a perovskite structure, which is a very stable structure. And here you can see the redox cycling in the TJ with a lot of these materials. You see it is very stable, it has a very good oxygen transfer capacity. And also you see here, you see no different colors here. You see just a gray color. It's very homogeneous in the material structure, and it doesn't decompose very much after use. So this is a very stable oxygen carrier material, and it could be a very good candidate. Then we also evaluated some manganese ore from China. And one of the ores was selected as the best one, which we call LY. And from the lab test, we decided to produce 1,900 kilo of this material in China and ship it to Europe for pilot testing. So this was this was a rather long process, but we managed with very good help from Tsinghua. It was thermally treated, crushed and milled in Hunan province. Then it was sealed in the Luoyang, Henan province, and then it was shipped from Shanghai to Europe for testing in our pilot facilities. Okay. So then I go a step up in the screening. We have this batch fluidized bed unit at IFPN. Then we are still at the lab scale, but we are now approaching at least a solid fuel, pet coke. So we can inject pet coke into this chamber here, where you have a bed of oxygen carrier. You can supply different gases. You can oxidize with air. Then you can supply some different fuel gases if you do gas as fuel cycling, or you can inject pet coke from the top and measure the outlet. Different operating conditions. This is an example of screening in the fluidized bed unit with the ilmenized T1 and T2. As I said, we originally discarded the T2, but as I forgot to say here, is that when this test was done for the perovskite, we observed some sulfur adsorption on the surface, and this deactivated the material. So we decided to now go further with this material for the pet coke case. Therefore, we went back and had a further look at this ilmenite T2, what could be the reason for the problem with agglomeration. And it was delivered dry. There were dry tests with methane, and it was not exactly the same as the other ilmenite. So by adding some surface steam, we observed no agglomeration anymore. And by doing this, we could solve that problem. However, we also lowered a little bit of fuel conversion. As we see here, the two curves here are with the steam addition, the upper curves without steam addition. But however, we are still within the design limits. So with this very important result, rather late in the project, we found that we could still go for this T2 ilmenite. IFDM 10 kilowatt unit, we have already talked about that a little bit, so I should just tell the main conclusion. It was tested with ilmenite and with manganese LY ore, with both gaseous fuels and with petrol, and the ilmenite performed better. So based on the extensive testing here, it was chosen before the MNLY. So the next pilot unit is the 150 kilowatt unit at Sintef, and it's based on two circulating fluidized bed loops that are just connected together. That is the main design philosophy here. We don't have L-wells, we have loop seals. And yeah, you see some pictures here. So the main difference of this unit compared to the European configuration in Cheers is that we have much less residence time in the fuel reactor. We do not have a carbon stripper, so we should expect poor carbon capture efficiency for fuels like petrol. However, it's a rather simple design. So, in any case, it will give very realistic testing of the oxygen carrier because it will be here in an environment which is autothermal. We don't have any supporting heat. It's autothermal. We have high velocities, high temperatures, and we have the relevant fuels. So it's still valid to test the oxygen carriers for the Cheers project. So these are the two ilmenites, different size fractions, very small. T2, which is the larger one, and the manganese ore. And these are the fuels that we tested. So the main goal was to test with petrol, and the petrol is also from China. It's the low sulfur petrol that Professor Lee showed in his table. Two different size fractions, and then we also tested with biomass, both in different variants. And I just showed this figure of result. This is the carbon capture efficiency. So what we see here is that in our unit, with this rather simple design, when we are operating on biomass fuels, all the three oxygen carrier candidates can give us very good results, very high capture rate in fact. But what we see here is that when we start to fire petcoke, this breaks down. We don't have the residence time needed, and we don't have the carbon stripper needed, and this is exactly what we have in the European configuration in the Cheers project to manage such a difficult fuel. Yes. Then I will give the word to Liu Wei.